So we were talking about the pre-calculus Edgenuity section 6.4, which is called Determinants. We have two objectives. The first is to evaluate determinants of 2 by 2 and 3 by 3 matrices. And the second is to apply determinants of matrices to solving problems. So let's get started with some example problems. I want to first get started with just a notation thing. There are two ways to denote that we are taking the determinant of a matrix. And you'll see this in the video also. You can write the matrix with just straight bars, and that is actually saying to take the determinant, or you can write DET at the beginning and put the matrix after it, and that is also saying to take the determinant. So when we take the determinant of a 2 by 2 matrix, it's pretty straightforward. And let me show you here. I'll show you with two different colors. You multiply the diagonals like that and like that, and then you subtract them. So you do these two first. So we'll do 5 times 10, and then minus these two multiplied. And so you do 1 times -1. So then I've got 5 times 10 is 50. I'm going to change this minus to a plus negative. I tend to do that a lot. It just helps me keep track of what's positive and what's negative. So plus, and then -1 times -1 is +1. And so the determinant is 51. So there's one. Pretty, I hope, pretty straightforward. Let's do the next one. Same thing. Multiply the diagonals. That one first. This one second. And then subtract them. So 2 times 9 minus 4 times -3. Again, I'm going to change the minus here to a plus negative. Helps me keep track of what's negative and what's positive. And 2 times 9 is 18, plus -4 times -3 is +12, which gives me a determinant of 30. I'll pause here for a moment to see if there are questions. Any questions, you can unmute or put them in the chat. I can also come back to this board if there are questions later. All right. There being no questions, I am going to move on to the next board. All right. So a 3 by 3 matrix is not as straightforward to get the determinant. Okay. So let me show you how this kind of works. You take the top row, and then you use the determinants of the 2 by 2 matrices that you can create without the top row and without the column that particular element of the matrix is in. So for example, for the first one, we're going to take that one, which cuts out that column, and then we're going to take the determinant of that 2 by 2 matrix. Okay? And so I've illustrated that down here. So that will be 1, oops, let me do that a little bit better, 1 times, and then we need to do the determinant of this matrix, which will be 1 times 1 minus 6 times 3 and then you subtract between the first two, so minus like that, and then we move on to the second column in the first row, that is to say element 1, 2, and we ignore that column, and so we use these numbers and these numbers to make the next 2 by 2 matrix, which I have illustrated here. So that will be 2, which is that 2 right there, times the determinant of that matrix down there, so 4 times 1 minus 6 times 0, and then you alternate to the next one and you put a plus. So we had a minus here, and then the next time we have a plus. And it actually works out that you can do this for even larger matrices with sort of the same technique, and you just keep alternating. You go minus, then plus, and then minus, and then plus, over and over again, just like if you remember Pascal's triangle, it's same idea. So then finally we go to the first row, third column. We ignore that column and we make a matrix out of the other parts of the second and third row, and so we wind up with this. So we get plus 3 times, and then it'll be 4 times 3 minus 1 times 0, just using the diagonals again. And then you come up with answers for all of this. So the first one's pretty simple. It's 1 times 1, which is 1, minus 6 times 3, which is 18. So 1 minus 18 will be negative 17 times 1 is still negative 17. I hope you were able to follow that. If not, let me know. And then minus, and then 4 times 1 is 4. I'm doing this part right here. And 6 times 0 is 0, so 4 minus 0 is 4, and times 2 is just 8. And then plus, and then I'll do this one here, which is 1 times 0 is 0, so 4 times 3 is 12. 12 minus 0 is 12. 12 times 3 is 36. And then we start putting things together. Let me change that minus 8 to a plus negative 8, because then it's really obvious that negative 17 plus 8 is, what is that, negative 25, I think, plus 36 looks like 11 to me. And so we get the determinant equal to 11. So that is the determinant of a 3 by 3 matrix. However, as you can see, this is pretty clunky, right? This is pretty, this takes a whole lot more work than the 2 by 2 matrices. Let's do it one more time just to see. So to find this determinant, we take the first element in the first row, first column element, and do that times, and then ignore that column and make a matrix out of the rest of the bottom stuff. So we're never making matrices using the top row. Okay? So then I'm worried about the determinant right there of that 2 by 2 matrix. So that'll be 1 times 1 minus 4 times 1. And then put a minus and use the next part. So 2 times, and then ignore those and make a matrix out of the rest of it and take that determinant. So 1 times 1, that is 1 times 1 like that, minus 4 times 0 like that, 4 times 0, and then alternate to a plus and go to the third column, so 3 times, and then ignore that one, so that you're dealing with that 2 by 2 matrix, and 1 times 1 minus 1 times 0. And then you do all the calculations. That's 4 times 1 minus 4 is negative 3, minus 2 times 1 minus 0 is 1, plus 3 times 1 minus 0 is 1. And let me change the minus to a plus negative, and we've got negative 12 plus negative 2 plus 3, which is negative 14 plus 3, which is negative 11. All right. So that's getting 3 by 3 matrix determinants. And I'll give you a moment to look at that. But then I'm going to tell you something that should help with this. And that is, there's a good matrix calculator online, and I talked about this before. It is meta-calculator.com, and if you go to that website and then choose the matrix calculator, there's a good matrix calculator on there. Not only is it good, but its functionality is fairly similar to the functionality of the matrix calculator that they give you on Edgenuity. So hopefully that helps as well. All right, let's move on to section 6.5, matrices and their inverses. And there's only one objective here, to find the inverse of a matrix. So let's do some problems from this. Let's talk about how to find the inverse of a 2 by 2 matrix. One thing you want to note, and you'll see why here, if the determinant is 0, there is no inverse to the matrix. Some matrices have inverses, some don't. And you might also notice that we're only dealing with square matrices here. That's because the only matrices that have determinants and might have inverses are square matrices. Okay? So if we have a pretty generic 2 by 2 matrix, A, B, C, D, the inverse matrix of that, denoted by A inverse, A to the negative 1, is equal to 1 over the determinant. That's why the determinant can't be 0. And that distributed to a new matrix where you switch these diagonals, and then you take the opposite signs of those diagonals. Okay? So I hope you can see that illustrated well here. I'll let you take a look at that and pause to see if there are questions. All right, there being no questions, let's go on and do an actual problem, okay? Let's talk about what the value of this variable would have to be in order for the two matrices to be inverses. Now, when Edgenuity has you do this, honestly, they haven't given you the inverse matrix formula yet, which I'm not sure why they wouldn't do that, but they are looking for you to actually multiply the two matrices and have some insights that way, which is perfectly fine. By the way, when you do multiply a matrix and its inverse, say for a 2 by 2 matrix, you get a matrix that is what they call diagonal and only has ones. They call this the identity matrix, denoted by a capital I. So just something to keep in mind there, something that they will tell you in the Edgenuity video. So I'm not going to harp on it too much. But, so let's call this one A, and let's call this one A inverse, the inverse of A. So what that would mean is that if we take 1 over the determinant of A and then multiply it by the new matrix where we exchange that diagonal and give the opposite signs to that diagonal, then we'll be able to calculate A inverse. And then it should tell us directly what that should be. So the first thing we got to do is get the determinant of A. I'll do some side work here. So determinant of A equals, well, that would be -3 times -1 minus 1 times 2, which is +3 minus 2, which is 1. Well, that's pretty convenient. So now we have 1 over 1 times all of this stuff here. And then we just got to multiply it by 1. Well, that's distributing a 1 is super easy. And so we have that. And that means that the x falls in that position. So x has to equal -3. All right. So I hope that helps. I'll give you a moment to look at that. See if there are any questions. We're almost done here. All right, there being no questions, I'll move on. All right, so here we're just going to find the inverse of this matrix A, this 2 by 2 matrix A. And we're just going to do the same thing. A inverse equals 1 over the determinant of A times the new matrix where we exchange the diagonal there and make opposite signs for the diagonal there. So I need the determinant of A before I can do anything else. So that looks like 4 times 2 minus 2 times 3 which is 8 minus 6, which is 2. So then A inverse equals 1 over 2 times this new matrix that gets me to the inverse. And now I just got to distribute that 1/2 to everything. 1/2 times 2 is 1. 1/2 times -2 is -1. 1/2 times -3 is -3 over 2. And 1/2 times 4 is 2. And that is A inverse. I'll pause for a moment to let you look at that, see if there are any questions. All right, there being no questions. One last piece of advice. If they ask you to find inverses of 3x3 matrices, use MetaCalculator or their matrix calculator. Some technology. It's not impossible, and it's actually a sort of similar process, except for more involved. But honestly, matrices are part of the foundation of computer programming. And so it's very rare to do this matrix stuff all by hand. What we really do is we want to know the inner workings, we want to know how they work, we want to understand how they work, but ultimately we can program a computer to do these. All right? So that is the end of these two sections. Thank you so much.